Hello everyone, let's go ahead and take a look at integrals that produce inverse trig functions. Now before we go ahead and take a look at how to produce the inverse trig functions through integration, let's just review the derivatives of the inverse trig functions. So if we have y is equal to arcsine of x, we come up with d of y over d of x being equal to 1 over the square root of 1 minus x squared. And if we have y is equal to the arctangent of x, then d of y over d of x is equal to 1 over 1 plus x squared. Now, the integral rules, which we have here, is going to be the square root of 1 over a squared minus u squared d of u being equal to the arcsine of u over a plus c, and the integral of 1 over a squared plus u squared d of u being equal to 1 over a arctangent of u over a plus c. Okay, now what we want to do is we want to be able to go ahead and prove this particular one here, and so let's see how it's done. So in the particular proof, what we're going to do is we're going to take a look at the original integrand, which is this part, and what we're going to do is we're going to try to get it to look like this. And in order to do that, I'm going to go ahead and multiply both the numerator and the denominator of this by 1 over the square root of a squared. So multiplying both the numerator and the denominator by that, I come up with 1 over a, because of course that simplifies to 1 over a, and that's just going to be a scalar multiple, times it by the integral of 1 over, now if I distribute this to there, what I'm going to come out with is a squared over a squared, which is of course 1, minus the u squared divided by the a squared, which of course I can rewrite as the u over a quantity squared. Now if I go ahead and let z be equal to u over a, I get d of z is equal to 1 over a d of u, and I get a d of z is equal to d of u. And so if I go ahead and do that substitution here, everything is going to be in terms of z. And if I go ahead and I multiply the 1 over a times by the a, that of course is going to cancel, and I get a simplified form looking like this. Now, of course, the nice thing about this is exactly the same form as that. And being that we know that integrals and derivatives are inverse operations of each other, then I know that this is going to produce the arcsine of z plus c. And now we need to just go ahead and make sure that we resubstitute back into the value of our expression here the original variables that we started off with. And we know that z is equal to u over a, so we know that this is going to be the arcsine of u over a plus c, and you are done. So I invite you to go ahead and take a look at the proof, try that on your own. You should be able to go ahead and do it following the same type of reasoning that we just shown there. Okay, we want to go ahead and also take a look at some applications now. And there's two primary applications for the integrals that produce inverse trig functions. So here we go. If we take a look at the integral of x plus 2 over the square root of 4 minus x squared d of x, if we didn't know how to integrate with, if we didn't know the integral rules to produce inverse trig functions, we'd be stuck. We wouldn't know what to do. You can't do a u substitution, a straight u substitution for that. But notice what happens is that if we break this up into two different integrals, then what we can do is we can actually solve for the original integral. So notice that this is going to be the integral of x over the square root of 4 minus x squared d of x plus 2 times the integral of 1 over. Now I've changed this to 2 squared, okay, minus x squared d of x, so that we can more readily see the inverse sign. Now in this case over here on this particular integral, I'm going to use a u substitution of 4 minus x squared, and I can come out with these particular, the d of u equal negative 2x d of x. Solving for the x d of x, I come up with negative 1/2 d of u. So I can change this now all in terms of u, which would be negative 1/2 times the integral of 1 over root u d of u. Now in this particular case over here, again I've readily identified what a was, and that's 2, and also readily identified what u was, which is x. So now I can very simply just go ahead and substitute into the arcsine. And so this is going to be 2 times by the arcsine of x over 2 plus c. Now we just need to do a little bit more on this left-hand integral here. to make sure that we can actually integrate. So I got negative 1/2 times it by 2u to the 1/2. And again, I need to go ahead and resubstitute so that everything is in terms of the original variables. And so I got the negative root of 4 minus x squared plus 2 arcsine x over 2 plus c. So that is going to be the integral of this, the result of this particular integral. Okay, and then the other case is when we need to go ahead and complete the square. Notice that if we have a quadratic in the denominator, what we can do is we can get it into a form that will hopefully produce the inverse tangent. So what I have here is the x squared minus 4x plus 7, rewritten here, right there, this. And then notice, in order to complete the square, I take the coefficient of the linear coefficient, linear term, divide that by 2 and square it, so I got negative 4 divided by 2, that's going to be a negative 2, square that, that's 4. Add and subtract that to the expression to make it equivalent. And then I take the first 3 terms and complete the square. And then notice again that here, negative 4 plus 7 is going to be 3. I'm going to change that to the square root of 3 squared, so that again, I can more readily identify what the value of a is. So I'm going to rewrite this as the integral of 1 over root 3 quantity squared plus x minus 2 quantity squared d of x. And then if I go ahead and use a u substitution, then I can come up with this expression here, which is easily identifiable as the arc tangent. So what I come up with is this, and then of course we need to go ahead and make sure that our original variables are in the final expression. Okay, so just to summarize again, by knowing the rules of integration that produce inverse trig functions, we can now attack different types of integrals which we couldn't before. And all we have to do is remember our 2 integral rules in order to produce those inverse trig functions. So we'll take a look at some examples the next time in class. Until then, see you. Bye.